all the limits that we've done so far, we're looking at what's happening as x approaches a number from both sides. All right, we're looking to see if our fingers are going to touch if we were to trace along the graph from both sides as we approach whatever particular value of x we're interested in. Sometimes that is not always going to be the case, and sometimes the two fingers may not match up. So let's take a look at that here with this concept of a one-sided limit. So you see over my shoulder here we've got f of x is equal to the absolute value of x over x, and this is on your paper as well. And let's try and fill in this chart and look at the accompanying graph just to get a little more information about this function. So we know for starters that we cannot plug 0 into the function, because if we do, we have 0 divided by 0, and we can't divide by 0, so f of 0 is undefined, okay? But what about f, we'll work backwards, f of 10, all right? If we plug 10 in for x, would you agree that we have 10 divided by 10? Yes, okay, so obviously that's going to be 1, okay? What about if we plug 1 into the function? All right, well, we have the absolute value of 1 divided by 1, which once again is 1. And would you agree that whether it's 10, 1, a tenth, or a hundredth, or any positive number, we're always going to get a result of 1 because we're basically just dividing that number by itself. Okay, so we can put 1s here and here as well. Right? Now, what's going on when we're looking at our domain that's below 0? Okay, what about when x is negative 10? Well, when x is negative 10, all right, so f of negative 10, that's going to be the absolute value of negative 10 divided by negative 10. Right? What happens in the numerator to that negative 10? Exactly, it becomes positive. So we have 10 divided by negative 10, which produces an answer of negative 1. Okay, and how about with negative 1? Will it be the same thing? Yeah, because we're going to have the absolute value of negative 1, which again becomes positive. And in the denominator, we're staying negative. Positive divided by a negative is a negative. So we get negative 1 here. And in fact, we'll get negative 1 for any input that is negative. So what does this do for the graph? Well, the graph is actually pretty simple. Just a pair of lines, or a pair of rays, actually. If we look at when x is negative, y is negative 1. Well, here's negative 1. So that means all of our points are right down there. Okay, and if we were to kind of connect the dots, then we have that going on for our negative input. Okay, now we have an open circle there on the y-axis because our function is not defined at x equals 0. And then as far as our positive results are concerned, well, we have the same thing happening. We have a whole bunch of points that are 1 unit above the x-axis, and when we actually put them all there, we have our graph, and once again, we have that open circle right there on the y-axis. Okay, so we have a couple of things here for starters. Let's go back to what we know already. We know that a limit exists if our fingers are going to touch each other as we approach the value we're interested in. Or if we're interested, if I were to ask you for the limit as x approaches 0 of f of x, all right, well, if we go to our graph, we see that as we approach from this direction, we're heading up here. As we approach from that direction, we're heading down there. My fingers don't match up. The limit does not exist. Okay, and the table verifies that. Because again, when we looked at the table before, we needed the numbers to close in the F column or row, depending on how you made your table, to basically squeeze in on a particular value. Well, values from the right are at 1, and values from the left are at negative 1. They're not closing in on a particular value. So again, that proves that our limit does not exist. So I actually don't want an equal sign right here. I'm going to say does not exist. Okay, so the limit as x approaches 0 does not exist. But there are some sublimits which do exist. Okay, and you see these on your paper as well. What about the limit as x approaches 0 from one direction only? Let's take just from this side, a one-sided limit. All right, so as x approaches 0 from the right only, now I don't need both fingers to take a look at both sides. I'm not interested in from the left. I'm only interested in from the right. And as x approaches 0 from the right, my finger is heading towards a vertical value of 1. So that limit does exist. So what's the notation for it? It's still the limit as x approaches 0, but we're just going to put a little plus notation above it. Okay? And that represents from the right. So the limit as x approaches 0 from the right of f of x is equal to 1. Conversely, the limit as x approaches 0 from the left, that's this direction only, will be negative 1. Well, if there's a plus superscript to represent from the right, we're going to have a little negative superscript to represent from the left. So the limit as x approaches 0 from the left of the function will be negative 1. Okay? And if you flip over your paper, you'll see a very important statement at the top there that basically says the only way that a limit is going to exist is if the limit as x approaches the number from the right is the same value as the limit as x approaches that number from the left. In this particular case, from the right is 1, from the left is negative 1. It's not the same number, which verifies that the limit does not exist. We need to see the same number in both of these cases in order for the limit to exist.